Okay, so in this problem we are asked to determine the electric potential and the electric field due to three fixed charges at a specific point. Now the first thing I would do before starting anything is choose our coordinate system. However, in this problem the coordinate system is given to us. So we have our conventional x-axis and y-axis. So we don't have to worry about that. Now notice we are given all numerical values. When solving physics equations, I prefer to use variables, and so let's label all of these quantities. So let's call this charge Q1, this one charge Q2, Q3, and our distances, let's call this x, call this y, and call this negative y. Alright, so let's begin with the electric potential. So the formula, which you can probably find in your book, for the electric potential at a specific point is 1 over 4 pi epsilon naught times Q over R, where Q is the charge and R is the distance between that charge and your point of interest. Now notice that the electric potential is a scalar quantity. That means it has no direction, so it is not a vector, and we don't have to deal with the more complicated vector operations. And so in this case, where we have 3 point charges, we can simply add the contributions of each to the electric potential. And so the total electric potential will be 1 over 4 pi epsilon naught, or excuse me, the sum from I equals 1 to 3 of 1 over 4 pi epsilon naught Q sub I over R sub I. And so it's going to be the sum of each of the contributions. Let's rewrite that. So let's put the constants outside of the sum. So that'll be 1 over 4 pi epsilon naught times the sum and now let's write it out. Times Q1 over R1 plus Q2 over R2 plus Q3 over R3. Now we need to write R1, 2, and 3 in terms of our known quantities. So let's do that. So not Q1. So for the first charge, it's going to be Q1 over R1. So what's R1? R1 is the distance between Q1 and our point of interest. So that's going to be this distance right here. Let's draw a dotted line for that. And notice it forms the hypotenuse of a right triangle. So the distance here will be, using the Pythagorean theorem, the square root of x squared plus y squared. And so let's plug that in for R1. Now for the second charge, it's going to be Q2 over R2. So what's R2? Well, R2 is given to us. As you can see, it's a distance between Q2 and our point of interest. And that distance is x. So we'll plug that in. And now for the last one, Q3 over R3. So R3 is going to be the distance between Q3 and our point of interest. again, using Pythagorean theorem, we get that R3 is the square root of x squared plus y squared. And that is the equation of our electric potential in terms of the charges Q1, Q2, Q3, and x and y's. So now you can simply plug in the numerical values and you will get your answer. I will leave that to the end. But first, let's solve for the electric field. So, the electric field, the equation you can find in your book, is going to be E equals 1 over 4 pi epsilon naught times Q over R squared times R hat. Now notice that unlike the electric potential, the electric field is a vector quantity. So it is not as simple. When we add them, we need to take into account their vector components. In this case here, the formula, the arrow over the E indicates that this is a vector quantity. Also, the R hat unit vector. This unit vector is called R hat because it is directed, because what this is saying is that the electric field vector is going to be directed along the direction of R. So R is going to be the line connecting Q, the charge Q and the point of interest, and R hat is going to be pointing in a direction along that line. So either away from the charge or towards the charge. A useful thing to do when dealing with vector quantities is to separate the vector into its components. And so that's what we're going to do now. So let's separate the vector E, and let's say that it's going to be the x component along the x direction plus the y component of the electric field vector times its corresponding unit vector. Right? And so now we simply need to find what our x component of the electric field is. Now, there are several ways you could do this. You could go through this problem very algebraically and just using the equations and plugging in the values that you find for the equations. But we can also make this process a little bit easier. In many physics problems, you can use the symmetry of the problem, some sort of geometric arrangement that allows you to eliminate certain quantities, and that makes it a little bit easier to solve. So it's kind of like taking a shortcut, and it's a very useful thing. That way you don't have to go through a really long problem, really long equations, and potentially get them make a math mistake. And so the way that I'm going to do this is I'm going to simplify the problem as much as possible using symmetry. Okay, so the x component of the electric field is going to be, so the total electric field x component is going to be the sum of the electric field from charge 1, its x component, plus the x component of the second charge, plus the x component of the third charge's electric field vector. Okay, now let's first sketch our vectors. So let's just kind of think about it for a bit. Q1 it has a positive charge of 20 nanocoulombs, and so its electric field vector is going to be directed away from that charge. So we're going to draw that as a vector here at our point of interest, with the tail at the point of interest. So basically like a free body diagram at this point. And we'll call that E1, vector E1. Now E2 is going to be also in the positive direction, and it's going to go along the x direction, right? Because remember, r hat indicates that the direction of the electric field is going to go along the line connecting the 2 points, the charge and the point of interest. So we'll call that vector E2. Now for charge 3, notice that charge 3 is negative. And so our r hat is going to be negative. So instead of going out this way, it's going to go aiming towards the charge. All right. Now notice that this angle over here, angle theta, is equal to this angle here, angle theta. And why is that? Well, these are essentially the same triangles over here. So by symmetry, we know that these two angles must be the same. Therefore, their corresponding x components are going to be the same, but in opposite directions, as you could see. This one, because of the negative charges, its x component is directed along the negative x direction. And this, and the electric field from charge Q1 is directed in the positive x direction. And so they're going to be the same, but in opposite directions. And so essentially they're going to cancel. And so I'm just going to show that by crossing them out here. So we're left with E sub x equals E sub 2x. Now notice that Q2 and our point of interest are connected along the x-axis. That means that the electric field contribution from Q2 is going to be entirely along the x-axis. And so essentially E2, the full magnitude of E2, is the x component also. And so E sub x is really just the electric field due to charge 2. So we get that E sub x is equal to 1 over 4 pi epsilon naught Q2 over the distance squared, right? So the distance is x, the distance from charge Q2 to our point of interest is x squared. The square term comes from our electric field formula. Alright, so now we're going to do the same, but in the y direction. So let's call that E sub y. And again, it's going to be the sum of all three contributions. Yeah. Okay, so now the first thing we notice is that we can immediately eliminate the y component of E2. The y component of E2 is 0, because as we mentioned before, the entirety of the electric field vector from Q2 is going to be directed along the x-axis. So there is no vertical component, right? Theta of E2 is 0 degrees. And so we can cancel that out because it's 0. So now we have that E sub y is equal to E1y plus E3y. Okay, now notice something else. Remember, by symmetry, the x components were the same, but in opposite direction. Notice here that our y components of E1 and E3 are also the same. They're pointed downward, so they're in the negative direction, and they're going to be the same magnitude. And so we could say that E1y is equal to E3y. And so essentially it's just going to be, it's going to be like saying E1y plus E1y. And so that's just going to be E. And so we're just going to get that the total y component is going to be 2 times E1y. Right? Because the contributions from E1y and E3y are the same. And so we could just, to make it easier, we could just multiply our E1y quantity by 2. So now what we get is, so let's break down our E1y. E1y is going to be E1 times sine of theta, right? So that's going to be our y component. It's going to be the magnitude of E1 times the sine of theta, right? That's going to give us this vertical component right here that we want. And so now, putting it all together, E sub y is going to be 2 times E1, which is going to be 1 over 4 pi epsilon naught times Q1 over the distance squared, right? So the distance squared, that cancels the square root. So x squared plus y squared times the sine of theta. So the sine of theta is equal to opposite over hypotenuse, right? From SOHCAHTOA. From vertical angles, this is also theta, right? And so we get sine of theta is opposite, which is y. But notice it's in the negative direction, right? So it's going to be negative y. Negative y over the hypotenuse, which is the square root of x squared plus y squared. And now we put it all together. So we get that our vector E is going to be 1 over 4 pi epsilon naught times Q2 over x squared in the x hat direction minus, right, this is the minus from the y, minus 1 over 4 pi epsilon naught times 2 Q1 over x squared plus y squared to the power of 3 halves in the y hat direction. So now you can plug in your numbers into that equation. And now you can plug in your values. Make sure you convert everything into SI units so that you don't have to be dealing with all the dimensions. So change your centimeters into meters, as I did. Also make sure that your numbers make sense. So remember we had a negative quantity for our electric field y value. And so we would expect it to be pointing down, right? This would indicate that the electric field vector is pointing down. And it's pointing to the right also, as we would expect, so it's positive there. And that's pretty much it. So thanks for watching.